All right. Good afternoon, everyone, and welcome back to another discussion hour. Today we'll be discussing the contents of week 8. Uh, and as I said, we stopped at, you know, s- so what we are doing is we are studying the transient heat transfer scenario in the context of conduction heat transfer, and we stopped at looking into a case where the temperature of a body was varying with time, uh, as and when we marched forward with time, but we assume that the temperatures were spatially uniform. That is, the temperatures were not a function of the coordinates, to be precise, which we call it as a lumped body. And this was the main agenda of discussion in the last week's discussion hours. Today we will proceed from where we stopped in the last discussions. And we will start today by discussing something which is known as a semi-infinite solid. And as we will proceed, you will see that this is kind of, an opposite end of the spectrum to the case that we discussed in the previous week, where, I mean, you will see very shortly that in case of semi-infinite solid, if you are trying to understand the transient heat transfer scenario, you cannot, disregard the fact that the temperatures of the body will remain spatially uniform. In fact, they won't, and this is the prime interest. That is how the temperature essentially varies with x, that is the distance, and time is the prime, point of investigation in case of semi-infinite solid, which is not the case when we are looking into the lumped capacitance model, where we just said that the temperature was just a function of time, which essentially reduced the heat diffusion equation into an ODE, if you remember. And we looked into the cases how that ODE was solved. For instance, if there was no heat generation in case of the lumped body, we simply, came up with an equation which governs the temperature distribution of the body with time, which was just T minus, you know, T minus T infinity by Ti minus T infinity is equal to exponent of minus T by Tc. This was the form that we studied, where, the term inside the exponent, you can express this in terms of various, the argument can be expressed in terms of various forms. For instance, you can also write that in terms of the Bio number and the Fourier number, and these are the things that we saw. But the essential difference, as I pointed out very shortly, was that the temperature remained uniform in space, and the temperature of the body was just a function of time, which, reduced the PDE into an ODE basically. But today, as you will see, we will basically be dealing in PDEs, because now in case of semi-infinite solids, essentially your temperature will become a function of the coordinate x and also time, which means that now we are dealing into a PDE, and we will, and in fact you have seen, I mean, in the lecture series you saw a glimpse of how to solve that PDE, considering the fact that it's a semi-infinite solid. And we will start today's discussion by giving a glimpse of this semi of the heat transfer analysis in semi-infinite solids. And then, proceeding forward, we'll be looking into a problem, how to deal with this solution of the form that we will see very shortly for the case when we have a semi-infinite solid. And then, as you can see from my screen, we will be ending the discussions on conduction heat transfer for this course by discussing a different approach, which we call it as the numerical methods for solving heat transfer equations. And what I will do is that we will present certain approaches, which, basically they are known as discretized methods, where, the heat transfer equations that we solved previously, in analytically, that we solved the previous heat transfer equations, we will now try to see a different approach where we will be solving those equations. In fact, we will not be solving, I'll just give you a glimpse of how to solve those equations, how to solve these equations using the numerical technique. That is, we'll be discretizing. So primarily we'll just learn how to discretize the PDEs that we saw. And but the solution, as I said, this is not a scope of this course to discuss. This is not a CFD course where, you are primarily taught how to, solve problems numerically, but, just to, you know have the completeness, just for the sake of completeness, we will give you a glimpse. In fact, I'll give you a glimpse of, how to solve problems numerically. But as I said, this is just an overview that I will present for two cases. One is the 2D heat conduction equation, which we solved analytically using method of separation of variables. So I'll show you that how can we now solve that equation numerically, and also the case for a 1D transient heat conduction, which is the prototypical case of the semi-infinite solid. I'll show you how basically we can solve that numerically. So this is the agenda towards the later part of this discussion hour. And so we'll begin by discussing this semi-infinite solid. Okay. All right. So in order to present the problem, I hope you have just watched the videos of this week and you are all set to, write the assignment for this week's contents. So I hope uh, this quick recap will help you to understand things that you have already caught a glimpse in the lecture videos. Okay, so when I talk about this semi-infinite solid, you can think of this as a fact that we have a long rod. Okay, the length of this rod is very long, and so that's the reason why I have shown you with a dotted line. And initially you can infer that this rod, the temperature of this rod, I will denote this coordinate as my x coordinate. Okay, so I'll denote this coordinate as my x coordinate, which is in the direction of the length of the rod. And I say that the temperature of this rod at initially, that is at time t equal to 0 for all x, is some Ti, which is nothing but the ambient temperature of the rod. Okay, so I'm just setting up the problem statement for this semi-infinite solid. That's what I'm doing. Okay, now I say that this length of this rod is considered as L, and we consider L to be very much long. The reason why we are assuming this to be very much long will be you know cleared in very short time. But I'm saying this L is very much greater than 1, where L is the total span of the rod. And I say that initially the rod is at a temperature Ti, which is because obviously if you are not imposing any temperature to the rod, the temperature of the rod and the temperature of the surrounding will be will basically be equal to Ti. That's how the nature works. Okay, now what I say here is that at time t equal to 0 plus, that is in the next subsequent time, I say that one end of the rod, for instance this end, is exposed to a temperature T naught, which is much larger than, let's say, T infinity. In fact, it is larger than T infinity. That is something that you can infer. Okay, so I say that at time t equal to 0 plus, that is for all the other subsequent time at x equal to 0, which is the left tip of the rod, for all time I am saying that this is exposed to a temperature T naught, which is greater than Ti. Okay, and on the other hand, the other tip, you can say that the length of the rod is so long that the message that this left tip gets at time t equal to 0 plus, that okay, there is a temperature T dot which is now exposed to my face, is not readily transferred to the other end of the rod. And in fact, the length of the rod is so long, okay, and you can just assume that in all the other subsequent time steps as well, the length is so long that the ultimate message of the fact that the left face is exposed to a temperature T naught is not reached at the right tip of the rod, which is this face. Which means I can say that my T at x tending to infinity, in principle x tending to infinity, is nothing but the length of the rod. And because I say that the rod is too long, which means in principle we are kind of talking of a infinite, we are kind of talking of a semi-infinite body. That's the reason why the name semi-infinite body comes. And the implication is that at x tending to infinity for all time, I can still say that my temperature is Ti, even though there is a message that at the left face of the rod, it is exposed to a temperature T naught. The idea again physically is that the length of the rod is so long that the right hand side, that the right tip of the rod does not get the message that at the left face there is an imposed temperature T naught which is greater than Ti. Okay, that's the whole idea, and that is the implication of saying that the length of the rod is too long. Okay, all right. So now, at least from these two conditions, you you can infer that if you now plot the temperature variation of the rod, okay, as a function of x, which is its length, which is in the direction of its length, you can get two temperature points. Let's say this is T naught, which is the exposed temperature at T equal to 0 plus on the left face, and you can then say that the bottom temperature is Ti, which is the initial temperature of the rod. So you can infer that at any given time instant, let's say T, the temperature variation of the rod will be something like this. Okay. So this is the temperature variation of the rod, where I am plotting the temperature of the rod as a function of x and t against this x. So you can understand that only because the length of the rod is so long, only up to a distance, let's say x1, the message that the left face is exposed to a temperature which is greater than Ti is felt. Basically, let's say x1 is this distance, and this x1 is basically the length up to which, you know, the message of a disturbance is felt in the rod, basically. Okay, and this profile is for a given time, let's say t1. So in other words, in simple sense, you can say that at time t equal to t1, okay, the fluctuations in temperatures are seen up to a distance x1, and for all other subsequent distance from x1 towards to the length of the rod, which is at x tending to infinity, you know, the rod does not know that. So in other words, these portion of the rod does not know at all that there is a disturbance which is imparted on the left face of the rod. Okay, so this x1, so for instance, if I plot this for a given time, let's say t2, which is greater than t1, the temperature profile, from using a little bit of common sense, will be something like this. The variation will be, sorry, so I hope you can understand that the variation, the nature of the variation, although we don't know the actual profile. In fact, we know the actual profile by solving the PD, but at least till now you can infer that qualitatively this is what the variation will look like, and this distance, let's say, will be, let's say, x2. Okay, so where t2 is basically greater than t1. So you can infer that when, as you are marching forward with time, more and more portion of the rod is getting the information of the imposed temperature which is at the left face. So you can infer that at time t tending to infinity, this tip will basically ideally should get the information. So the right hand tip will only get the information of the fact that there is a disturbance at the left face at when time basically t going to infinity. So this is another boundary condition that you can use for this problem as well. But that boundary condition is kind of a trivial boundary condition, because you already know that the length of the rod is so long that the extreme portion, the extreme end of the rod, will get the information of the imposed temperature at time t going to infinity, basically. Okay, so you can now infer, more importantly, that these x1 and x2s are essentially functions of time. Okay, which means, contrary to the case where in lump body we assume that the temperature distribution inside the body was not a function of space, but here it is a heavy function of space. It is heavily dependent on space, because you can see that the message up to which the disturbance propagates, in technical terms, if you say, is dependent on at which so basically is dependent at which time we are looking into the so what you can say, so we are basically looking into the problem. Okay, So I hope you can understand. So in simple words, if you say your temperature profile in the scenario when there is a semi-infinite solid is dependent on x and t. Okay. Now this x1s and x2s, okay, so for instance this x1 x2s, these, as I said, these are functions of time. Okay, these are functions of time, and they are generally, described by a parameter which we call it as delta, and this is known as depth of penetration. And by now you can realize that this delta, which is the depth of penetration, is a function of time. Okay, because at time t equal to t1, the delta was equal to x1. At time t equal to t2, your delta is equal to x2. So what I was saying is that at time t equal to t1, your delta, which was a function of t, was equal to x1, and at time t equal to t2, your delta is basically equal to x2. Okay. In fact, I should just write this at x1 and this is just x2 because these are just coordinates in terms of the length. But the depth of penetration, as I said, for instance, this delta, uh, which is equal to x1 at time t equal to t1, and this delta is basically equal to x2 at time t equal to t2. This is indeed a function of x, meaning this delta is a function of this delta is a function of time. And so you can infer that the depth of penetration is indeed a function of time. All right. So given this information, you can precisely show that there is indeed a similarity that is going on between the coordinate x, okay, and the time t, that is the message up to which portion of the rod will get the information that there is a imposed temperature exposed to one of the phase is dependent on which time you are looking at. You are basically looking at the propagation of the disturbance, which means there is an inherent relation between this x and t. And that's the reason why when you are looking the solution procedure of this problem, there is this thing known as similarity approach, which you basically use to solve this problem, which says that there is which basically says that you can now define a similarity variable, let's say eta, which is equal to x by square root of alpha t. Okay, so this is so if you remember, this was the similarity variable that you defined in order to solve the governing equation. And the reason why I say it is that the similarity variable looks like this is because of the fact that the x that you are looking is dependent indirectly on at which time you are basically trying to understand that how much the disturbance has propagated. Okay, now before trying to actually understand why the similarity variable takes this form, and and basically you can show that this is nothing but so this square root of alpha t is actually proportional to delta, which is the depth of penetration, and we will show that very shortly. But before that, let's begin by actually trying to understand the governing equation which governs how the temperature distribution in this rod would look like. Okay, so as you know, the governing equation which governs the temperature distribution inside this rod is nothing but the heat diffusion equation, which if you write for the system would be del square T by del x2, and this is equal to rho Cp times del T del T. Okay, so this is precisely the governing equation uh, that governs how the temperature distribution inside the rod would basically vary. So you can infer, so first and foremost, you can infer that your temperature profile, which you are calling it as T, this is a function of x and T, okay? Which means that earlier to the case, in case of a lump body where your temperature is just a function of time, here it's a function of space and time. So it's kind of a PDE that you basically need to solve. Okay. And one more thing that you need to understand is the fact that these kind of PDEs, these are actually known as parabolic PDEs. So if you remembered, when we solved the the 2D steady state heat diffusion equation, which was just Laplacian of t equal to 0, I said that those kind of PDEs are known as elliptic PDEs. Contrary to that, the PDEs of this form, which is nothing but the 1D heat heat diffusion equation in transient form, this is known as a parabolic PDEs. Okay, I mean, we'll not go into the depth of why this is called a parabolic PDEs. That is not required at this point of time. But for your knowledge, for your general knowledge, I mean, you can at least try to understand the fact that these kind of PDEs, whose canonical form is of this type, is known as parabolic PDEs. Okay, so now you can write this equation as, if you just simplify, you can write this equation as del square t by del x2, that is equal to rho Cp by k del t, where you all know now that this k by rho Cp, this is actually known as alpha, which is the thermal diffusivity, and then you can write this as del square t by del x2 is basically equal to 1 by alpha times del t. All right, and this is the PDE which governs the temperature distribution inside the rod. Of course, we need certain boundary condition and an initial condition. So the initial condition is the fact that at time, for all x at time t equal to 0, the rod is basically at temperature Ti, and the boundary condition is the fact that at x equal to 0, that is at the left hand face, we are exposing the rod to a temperature T naught. Okay, and at the other end of the rod, you can say that when x basically goes to infinity for all time, you can you can infer two things, that your rod will now see. So basically you can say that when you are at the extreme right face of the rod, it is so large that the disturbance has not yet propagated. So you can say that this is basically equal to Ti. That's one way of saying that, and that's the implication. So as I said, this is the implication of a long rod. Okay, and that's the reason why this is called as a semi-infinite body. That's the reason why the word infinite come into the picture here. Okay, anyways, so we basically have PD denoted by equation 1, and for this PD, since there is a partial t by partial small t term there, we need an initial condition denoted by equation 1a, and two boundary conditions denoted by equations 2a and 2b. The reason why we require two boundary conditions is the fact that the variation in temperature is second order with respect to x and first order with respect to time. Okay, so now the question comes that how do you basically solve this equation subject to these two boundary conditions? And this is the point where actually we define the similarity variable eta, which I just stated a few minutes back, that eta is essentially related as x by square root of alpha t. So the reason why you are defining this similarity variable is because of the fact that the distance up to which, as I said, the distance up to which the disturbance has propagated is a function of what timestamp you are actually looking at. So there is an inherent relationship between the depth of penetration and the time t, and that's the reason why you can now define a single variable which will encompass the variations in x and t together. But the question that should pop into your mind is the fact that why there is this root over alpha t in the denominator. So we can also define eta. We could have also defined as eta we could have also defined eta as just x by t, or let's say x by t square or something like this. But the reason why we define this solely in this form will be clear if we if we try to scale this particular equation. Okay, if we kind of try to understand the order of magnitude of this particular equation. Okay, and we will see that very shortly. But until this point, I hope you understood the basic essence of this problem. I will not show the solution procedure by involving this similarity variable, because this was done extensively in this had been shown extensively in the week's lecture series. but I'll try to give you the flavor of why certain things come into the derivations involving this similarity variable. Okay. All right. I hope I hope you are with me until this point. Okay. So the question that I was trying to ask you is the fact that why do we choose only this particular form in the denominator when we are defining the similarity variable? But first of all, you could, I hope you also need to appreciate the fact that why are we basically defining this similarity variable? The reason why we are defining this similarity variable is the fact that if you substitute now, see what we are trying to do is, this was a PDE which has two, independent variables which were x and t, okay, and the dependent variable was temperature. So temperature was a function of x and time. Now what we are doing is we are trying to define a single variable which will encompass the variation of x and t. And the reason why you can do this, because there is an inherent relation between the depth of penetration and time t. Okay. Had your temperature, so if you cannot establish that inherent relation, okay, between that x, between the coordinate of the system and time t, you cannot use a similarity variable to solve your problem. That is the essence of defining a similarity variable. But if you little bit try to understand the depth of this problem, the reason why we define, and this is important as I feel, the reason why we can define a similarity variable in this problem is because my problem, if you try to understand, is so it basically does not have a distinct length scale here. Okay, because you cannot say that the length scale of this problem is L. The reason why you cannot say that the length scale of this problem is L, because you know if you pick L as the length scale, you should see substantial variation in temperature within L. But that is not the case in this semi-infinite solid, because the right hand tip of the rod doesn't know that there is a disturbance that is propagating from the left face, from the left tip of the rod, which means in no way you can choose L as the length scale of the problem. Okay. Whenever you encounter such scenarios where there aren't any defined length scale in your problem, the use of similarity variable comes into our picture, and we then define a length scale that is actually hidden in the problem. In this case, the length scale is basically this delta, which is the depth of penetration, and the similarity variable is essentially defined as eta equal to x by delta. Okay, so basically we pick that length scale where we can see substantial variations in the temperature. For instance, if I pick delta as my length scale in this problem, you can see that up to delta there is a substantial variation in the temperature. So delta is essentially the length scale in our problem and not the length of the rod, which is L. So in such problems, as I repeat, where the prescribed length scale, or you don't see any prescribed length scale into the picture, and the scenario when there is a prescribed length scale but you cannot use the prescribed length scale in defining the physics of the problem, in all these scenarios you can use similarity variable, let's say eta, to basically make the transition from the PDE to an ODE, as you saw in the lecture series. But the crux of using this similarity variable lies in the fact that the length scale, even if you have, or let's say in general you don't have a length scale in the problem, is when you precisely define the variable eta. Okay, I hope this is clear to you. So I'll write it down that if the prescribed length scale, or let's say I should write it down in this form, that if the prescribed length scale does not capture the variations in the variable of interest, which is temperature in our case, which is temperature T, as a function of x of t in our case. Or the other thing that if the problem does not have a length scale at all, in such scenarios, okay, we use the approach of similarity solutions. So these solutions, so this approach is known as the similarity solutions, and the variable that we have defined eta, this is known as the similarity variable. Okay. As I repeat, the similarity variable is chosen because we know that the depth of penetration and the timestamp where we are looking at the depth of penetration is indirectly related to each other. And the second thing, we don't have a defined length scale in this problem because the length of the rod does not convey the essential physics that can, or precisely we should say that the length of the rod does not capture the essential physics if we choose its length to be the length scale of the problem. So the essential length scale is actually delta, which is indirectly a function of time, and that's the reason why we are using the similarity variable. Now we'll show that your delta is actually proportional to alpha times t, and that's the reason why this factor, square root of alpha times t come into the picture going forward. Okay. So in order to show the variations in this penetration, so it's kind of understanding how the depth of penetration essentially varies with temperature. For that, we will pick the governing equation, which is del square t by del x squared is equal to 1 by alpha times del t by del t. Okay. So what we will now do is we will say that my temperature, which is the primary variable of interest that we seek to calculate, this scale says some characteristic temperature, let's say Tc. For instance, this Tc you can pick to be, the imposed temperature at the left face. It's your choice completely. Okay. So then what I can say that I can now define a non-dimensional temperature, let's say T bar. Okay. Which is the dimensional temperature T divided by the characteristic temperature Tc. In the same sense, I can also define a non-dimensional, let's say x bar, which is the dimensional x divided by the length scale, and we will pick the length scale now as the depth of penetration. Okay, where this delta, as I said, this is the depth of, penetration. So the reason why we are doing this exercise is that we are trying to understand the variation in this depth of penetration with respect to time. That's the thing that we are trying to analyze. Okay. So if you do this for all the variables, you can show that this del square t by del x square, this basically scales as Tc by delta square, because you can understand that there is one T here which will just give, which scales as Tc, because we have defined a non-dimensional temperature such that it is T by Tc, meaning that this T will now scale as Tc, and del x square will basically scale as delta square. Similarly, you can also show that 1 by alpha del T by del T, this will basically scale as Tc by alpha times some characteristic time, let's say small t. Okay. But since these two terms are equal, their scales will also have to be equal. And then we can say that, Tc by delta square, this should be of the same order. Remember, this is not equal. This just says that Tc by delta square is of the same order as Tc by alpha t. Okay. And then you can just infer that your delta square is of the same order of alpha t. Okay. And then you can just say that your delta just varies as square root of alpha. Okay. That is the reason why you choose that square root of alpha t in your similarity variable. Okay. I hope you can understand now why there is a square root of alpha t and not any other functional forms of these parameters. Okay. So you can then infer that the depth of penetration, that is delta, which is nothing but the depth of penetration of the disturbance. Okay, this is proportional to square root of alpha. This is proportional to square root of time. Okay, so now at least you know the profile between so at least now you know that the depth of penetration is proportional to square root of time, meaning that when you are increasing, and then also you can infer the fact from this graph that when you are increasing the time interval, to be precise, the depth of penetration also increases with x, and that's the reason why the second curve essentially looks something like this, because since t2 is greater than t1, your depth of penetration has also increased. Okay, and that's the reason why you basically have the similarity variable defined as x by square root of alpha t. Okay, now all you now need to do, and I hope you have just uh, saw this in the lecture series, is that you need to now transform this PDE into an ODE involving just this eta, because eta essentially encompasses the two independent variables x and t. So the idea of the similarity solution is that you define a similarity variable which will take care of the two independent variable, and then if you substitute the variations now. So basically what you need to do is you need to convert the del square t by del x square as a function of t and eta. So when you do this, you will see that your PDE will automatically, get converted into an ODE, and basically you just need to solve that ODE in order to get the temperature profile. That's it. And in the same spirit, you also need to convert the boundary conditions written in terms of x and t as a function of just t and eta, basically. For instance, you can say that, let's say at x equal to 0, my eta is basically 0. That is one of the boundary conditions that you can infer. And let's say you can also say that at, let's say, time tending to infinity, my eta basically is also 0. So this is so this is the way how you convert the boundary conditions in x and t into the boundary condition in eta, because now we are just interested in the variations of temperature as a function of eta, which is the similarity variable. I will not show the detailed steps here because we have already done this in the lecture series. I will just write down the solution of the temperature that you get upon doing these steps, and the final solution that you get is that your temperature, which is a function of x and t, minus T naught divided by Ti minus T naught, where Ti is the initial temperature of the rod. You get this as something which is known as ERF, which is the error function, by x times 2 alpha t. So this is the solution that you get. So this is the final solution that you get upon solving the ODE. So basically when you solve the ODE, you just get that T minus T naught by Ti minus T naught is error function of eta by 2, where you know that your eta is just x by alpha t. Okay, and that is where this, and that is from where this this argument basically comes, where this ERF, this is known as the error function, which is essentially defined as 2 by square root of pi integral 0 to z, where this ERF is an error function, and the variable used in this error function is z, where error function of z is defined as 2 by root pi integral 0 to z e power minus t square dt, where this t is nothing but any, so it's kind of a dummy variable that we are using for integration. Okay, so this is the definition of error function. So for instance, the error function of x by 2 root over alpha t will take basically this form. So it is just integral 0 to x by 2 root over alpha t, and then it is just sum minus, let's say, e power m square dm. That's it. That's the definition of error function of x by 2 root over alpha t. Okay. Now there is one more property. We also define something which is known as the complementary error function, which is defined as ERFC of z, and this is just nothing but 1 minus error function of z, basically, and this is known as the complementary error function. Okay. All right. So this is the final temperature profile that you get upon converting your variables to eta, which is the similarity variable, and then substituting, and then obviously transforming the PD into an ODE in terms of just T and eta, and then solving for that ODE basically. That's the final solution that you get upon solving solving the ODE. Right? Now written in terms of T and eta basically. All right, so this this is the final solution that you get, that is the temperature profile written in terms of the error function while solving the semi-infinite solid. But I believe you have tried to understand the physical aspect involved in the semi-infinite solid problem. For instance, the depth of penetration, why do we use a similarity variable, when do we use a similarity variable, taking into consideration of the fact that either we don't have a length scale defined in our problem, inherent length scale, I should say, defined in our problem. Because see, this delta is not the inherent length scale. This delta is the length scale that pops up into the picture because of the fact that your true length scale, which is the length of the rod, is unable to capture capture, in simple words, you should say, the physics of the problem. Okay, because the inherent length scale is absent, or the inherent length scale is not able to capture the variations in the temperature, you define kind of a length scale which actually is a function of time, but that length scale, which in this case comes out to be delta, this is essentially related to the timestamp at which we are looking at the picture of the problem. Okay, and that's the reason why you can now define a similarity variable eta, which will encompass this variation in x along with the variation in delta. Okay, and as I said, just by doing a simple order of magnitude analysis, you can show that your delta is proportional to your alpha times t, which is the thermal diffusivity and the timestamp t that we are looking at in this problem. Okay, and then I said that your job is just to convert this PD into an ODE involving just t and eta, and then writing the boundary condition in terms of eta as well, and some examples as I showed you how to convert the boundary condition how to convert the boundary condition from x and time to the boundary condition in eta. That's something that I showed you. And if you do that and then substitute into the PD, you will see you are solving an ODE, and a final solution of the ODE, as you have seen from the lecture series, basically comes out to be something like this, involving an error functions where where this is the definition of the error function. Okay, all right. So this was the whole picture behind this semi-infinite solid. And what we'll do is, in order to look into the application of this model, we will solve a problem involving this semi-infinite solid. The problem statement is there in your screen. So it says that a thick steel slab, okay, is initially at some temperature and is cooled by water jets impinging on its surface. The temperature of the jet is 25 degrees Celsius, and the jet maintains an extremely large, approximately uniform convection coefficient at the surface. Assuming that the surface is maintained at the temperature of the water throughout the cooling, how long will it take for the temperature to reach 50 degrees Celsius at a distance of 25 mm from the surface? So that's again a classical problem of a semi-infinite solid. So what it said is that there is a thick slab. Okay, so there's a thick slab. The thickness of the slab is so long that you can consider this as a semi-infinite body. And then what you are doing is, initially the slab is basically at temperature Ti. So your temperature Ti, which is the initial temperature of the slab, we will call it as Ti basically, is a function of x, and at time t equal to 0, this is basically equal to 300 degrees Celsius. So you are trying to cool this slab by spraying jets on its surface. So basically this is how you are trying to cool the slab. So these jets are being impinged on its surface, and due to the impingement of these jets, you are kind of maintaining the temperature at the left face of the slab, which we will now call it as T at x equal to 0 for all time at 25 degrees Celsius. That's what they have said. Okay, So that's the background information that they have given. Now they're asking is that how much time will it take for the temperature inside this slab to reach 50 degrees Celsius at x equal to 25 mm. So what they're saying is that if we now pick, so first of all I will call this dimension as my x. Okay, so what they're asking is that how long will it take for the temperature of the rod to reach 50 degrees Celsius at x equal to 25 mm. Okay, if I try to draw the picture graphically, this will be more clear. So what they are asking is that I'll again kind of draw the temperature variations of the slab as a function of x. So what they're asking that initially the slab was at 300 degrees Celsius, and the lower limit I could say it to be equal to the temperature at the left face, which is 25 degrees Celsius. So what they're asking is that how much time will it take for this temperature to reach 50 degrees Celsius at x equal to 25 mm. Okay, that's what they're asking. So basically they're asking you, so if I draw the plot, it will be something like this. So they are asking you that when x is at 25 mm, they are simply asking you about the time when your temperature will reach to 50 degrees Celsius. That's what they're asking. That's what the question is precisely asking us to evaluate. Okay, I hope you can understand from this graphical representation of the same. Okay, so we just need to calculate this time. Now, first of all, this is a semi-infinite body because you know that the right face of the slab does not know, or it does not have any information that there is a jet impingement which is trying to cool its left face, and it's kind of maintaining the temperature of this left face at 25 degrees Celsius in the subsequent times. Meaning that the depth of penetration, which in this case will be our delta, which will be a function of time t, is what we need to use, and we don't have a prescribed length scale in the problem. So this means this is the case of a semi-infinite solid, and in this case we can directly use the form of solution that we saw, which is nothing but the temperature, which is a function of x and t minus t naught divided by ti minus t naught, and this is equal to error function of x by 2 square root of alpha t. That's it. It is easy to substitute values, but first of all you need to understand that why in this problem we are using the concept of this semi-infinite solid. Number one, the first and foremost step is that from the problem statement we can infer that the right face of the slab has kind of no information that there is I should say that so the right face has no information about the propagation of the, so in technical terms I should say it as the temperature wavefront. Okay, this calls for so basically it says that the inherent length scale, which is the thickness of the slab, this does not capture the physics of the problem since it has no information on the propagating temperature wavefront. So this calls for a similarity variable eta, and we can now solve this using the approach of this similarity variable. Okay, and that's the reason why we have used the distribution of temperature, use the solution of the temperature distribution we get when we solve this similarity variable approach. The rest, everything is just straightforward. You just need to substitute x equal to 25 mm. In this case, your T naught is known, so this is 300. Your T naught is not 300. I'm sorry. T naught is basically the temperature of the left face, which is just the temperature of the jet, which is 25 degrees Celsius. Ti, which is the initial temperature of the slab, is basically equal to 300 degrees Celsius. X, you know, it is equal to 25 into 10 to the power minus 3 meters. Alpha, you can calculate by using the fact that your alpha is equal to K by rho Cp. And you know the values of K, you know the value of rho, you know the value of C, which directly means that you know the value of alpha. Just one variable you need to calculate, which is this. Substitute all the values, take the complement of the error function, and you should get, you know, the temperature at X equal to 25. Uh, I mean, sorry. So the temperature is also known because it says that at X equal to 25, your temperature is basically equal to 50 degrees Celsius. So what you need to do is that you know this temperature as well. And the only unknown that you need to calculate from here is just this time t. So so basically you know the left hand side. The left hand side is completely known. The X is known. The alpha is known. You just need to calculate this time t just by substituting the values. And there is a table which says that if you are kind of calculating error function of X and this is equal to a known constant, let's say beta, then there is a table in the, so actually this table is present in the book of Incropera, which is your textbook. You can basically calculate the X once you know so basically if you know that error function of, let's say, some X is equal to some, let's say, known constant, some beta. So if you know beta, you can basically, get the argument in the error function from that particular table, which is in the book of Incropera. You can just look into the table and basically calculate the time t from this problem. I hope this much is clear to you on how to solve problems using error function. Okay. All right. So this is just a simple problem involving this semi-infinite solid. I just gave you a glimpse of how to basically solve a problem considering that your body is a semi-infinite solid. And yeah, so just for you to just give you an idea, so as I was talking about the table, so basically you have a table which says that if your X varies as, let's say, something, the error function of X basically varies uh, in that following manner actually. So actually you just need to evaluate that integral. So that is already done in the table given in the book of Incropera. So all you need to do is just calculate this particular X. Okay. And then you can get the corresponding error function basically. Okay, I hope this is clear. We'll stop here because this ends the discussion on the semi-infinite solids, and I hope you can understand the physics behind it. And now we will proceed into the second aspect in this discussion hour, which is the numerical approach in heat conduction equations. Okay, but we will stop here for a couple of minutes, such that you can digest whatever we did in the previous discussion, in the previous 1 hour of discussion we had, and we'll proceed from this point onwards uh, in, let's say, 1 or 2 minutes. In the meanwhile, I'll just come by filling my mouth with some water. Okay. All right, guys. Sorry for the interruption. So let's begin. So this is the last topic of conduction heat transfer, and as I said, we will try to now see a different approach into solving the typical heat conduction equations. For instance, we'll look into the two scenarios. The first is the case of a steady 2D heat transfer equation and how to basically, solve that using a numerical approach. And the second case, if there is time, we will see how to solve the 1D transient heat diffusion equation. For instance, the case of a semi-infinite solid as we just now discussed. Okay. But first of all, let's try to understand that why there is a need, to solve, why there is a need to have a numerical approach into solving these equations. So for that, we will first, as I said, we will look into the case. So we will look into the case for a 2D steady, you know, heat diffusion equation. For instance, if you remembered, we kind of solved this problem using something which is known as the method of separation of variables, where there was a rectangular slab and the coordinates was something like this. So this was the x direction, this was the y direction, and we said that the temperature on the faces here was t equal to 0, it was t equal to 0 on these three faces, and on the top face we had temperature varies as varying as some a times x. Okay, so we solve this problem using the method of separation of variable, and the reason why we could use method of separation of variable in order to solve that problem is because of the fact that the temperature on these three faces, at least on these two faces, were uh, was kind of homogeneous, meaning that it was equal on these two faces. For instance, if I had temperature T equal to 10 degrees Celsius, 10 degrees Celsius here, we also as so we saw that just by using a simple transformation, we can use method of separation of variable. But this is not always the case we can encounter in real life situation, right? For instance, I can have a temperature here to be at some 80 degrees Celsius. I can have temperature on this face to be some at 100 degrees Celsius, on this face at some, let's say, 150 degrees Celsius, and here let's say some other temperature, let's say some ax plus, let's say 10 degrees Celsius. So we have a variation as well as a constant part. So this is how you encounter real life variations in temperatures in the boundary conditions for, let's say, the temperature variable here. Okay. Now, in that context, you cannot, first of all, you cannot use the method of separation of variables. So the method of separation of variable will basically fail there. And that is the reason why you need to have some other approaches which are kind of more generic in nature, that it can take care of any variations in the boundary conditions that we have. And one such generic technique is these numerical solutions that we will see. Now, at least you got an idea or a motivation why do we need to basically study the numerical approach. I understand that the analytical solutions are exact, they are very powerful, but their applications are confined to certain analytical limits. For instance, here the boundary conditions need to be homogeneous if you are kind of trying to apply the analytical approach in this scenario. In other senses, for instance, if you have a non-linear governing equation, let's say, you cannot apply the method of superposition of sorry, the method of separation of variable and the method of superpositions and all the analytical techniques that we learned. But the numerical approach will still work, and it is very much applicable even if you have a governing equation which is in general non-linear in nature. But we will not look into the non-linear equations here. Instead, we will look into the prototypical example of a 2D heat diffusion equation and how can we basically apply the numerical approach, the motivation of which, as I said, comes from the fact that there are certain limits where the analytical solutions are valid, and if you are trying to go beyond those limits, you cannot use analytical techniques, although they are very powerful. You cannot use basically to solve your problem, and then you need to resort to techniques like this numerical approach. Okay, so before actually trying to understand this numerical approach, again you saw that glimpse of how to do the discretizations and all those things in the the lecture classes, but again, I'll give you just a recapitulation of what you basically learned. Okay, so if you remember, what we basically do in a numerical approach is that we discretize the entire domain of interest. For instance, the the slab face here into certain. So what we do is we divide the entire domain into certain grids or nodes, as they call, as like, so what we do is like we divide this domain into to these grid points as this. So what we do is we kind of divide the entire domain into these grid points. So by grid points, I mean these blue dots that I have, drawn on the intersection of these lines, basically. So these grid points can be on the boundaries. The message of the boundary condition will be implemented on the boundary grid points, and the grid points in general can be on the faces as well. Okay. So if I kind of, so for instance, this is one such grid point that I'm drawing. So like if I kind of zoom in, if I kind of zoom in into this into this so basically I'm zooming in into these, how many into these 9 grid points, then the picture actually looks something like this. So I'm just zooming in this thing, and I'm just drawing this picture here. So what I'm doing is I'm just zooming this part and I'm drawing it here. So these grid points essentially look something like this. So okay. So what I'm doing is I'm just drawing these 9 grid points into in so basically I'm just looking at these 9 grid points. Okay. So the idea is that you are supposed to divide the domain into like m times n grid points. The more finer your mesh is, so this is known as a mesh. The more finer your mesh is, the more accurate your result is. And then what we do is I'm just trying to look at any generic grid points into this meshed domain. Okay. And what I now say is that this, let's say this grid point, I call this grid, the notation of this grid point, I call it as, let's say, m comma n. So this is the mth, kind of the mth row and the nth column uh, in the 2D structure that we made, basically. Okay. For instance, you are kind of like having m grids in X, and let's say you are kind of having n grids in Y, which means that in total you are basically having an m times n grid points. Okay. And I am just looking at a generic m comma n grid point. Okay. That's what I'm doing, which means that the grid point that is just to the neighboring right of this generic m comma n grid point is denoted as m plus 1 comma n, and this grid point is denoted as m minus 1 comma n. In the same spirit, the grid point which is just top and below the generic point m comma n is denoted as m comma n plus 1 here, and this is m comma n minus 1. Okay. So where is my this is just a generic grid, point. Okay. I hope you you have understood this so far. Now, the reason why you are doing this exercise, or the reason why you are dividing the entire domain into grid points, is that we will try to write down the PDE. For this case, it is just the Laplacian of t equal to 0, which is the PDE, because we already saw this in when we were trying to use the separation of variable. So what we'll do is we'll try to write down this PDE as algebraic equations on all the grid points that we have divided the domain into. Basically, since there are m cross n grid points, we are going to discretize the PDE, which is the Laplace equation, into m times n algebraic equations. So basically you have m times n grid points and you have m times n algebraic equations, and what you are trying to do is you are basically calculating the temperature at each and every grid points, is what you do in numerical approach. So now you understand that there are m cross n grid points, m times n grid points, and you are trying to calculate the temperature at these nodes basically, or grids. Okay, which means there are m times n grids, meaning that there will be m times n values of temperature at these grids, and also you will have m times n equations, algebraic equations to be precise. So m times m algebraic equations and m times n unknown values of temperature in the grids. So the number of equations and the number of unknowns, are the same. So it's a closed system, and basically you just evaluate the unknown. That's it. So it's so it just all boils down to the fact that you are solving algebraic equations having the same number of equations and the same number of unknowns. Okay, and the message of the fact that your faces are subjected to certain temperature is conveyed to these boundary grid points. Okay, and this is how this message will propagate to the interior grid points in case of numerical approach. Okay, that's the whole idea behind this numerical solution. Now you can ask me that I can just choose a grid like this, which is just a coarse grid, and then just calculate the temperature at just these few grid points, but then your solution will not converge to the analytical solution. Basically that's a coarse grid, which means that so basically this is an approximate model. So all the numerical solutions are kind of an approximate solution that we are doing, and you need to have at least a certain number of grid points to reach, so for the solution to reach to the to basically reach the actual desired value that it can basically take. Okay, so there is a term which is known as mesh independence. So you need to ensure that you should have sufficient number of grids that which will tell you that okay, so basically the solution that you get from that solution that you get by solving them numerically is correct enough, and increasing the more number of grids will not change the solution. Basically that is known as mesh independence, and we'll not be going into the depths of all these things because this is beyond the scope of the discussion in this course, but at least we will try to understand how do you basically discretize a given PDE or an ODE into an algebraic equation. Okay, for this let's say I pick now the generic governing equations which govern the temperature distribution in this plate, which is nothing but the Laplace equation, which is just del square T equal to 0. And if I write this in the form of a PDE, it is just del square T times del x square plus del square T times del y square is equal to 0. All right. So as I said, what you now need to do is we need to discretize the above governing equation. So the meaning of this term discretize is that you are now supposed to convert the PDE into an algebraic equation. Okay, but how do you do so? So this is where the concept of Taylor series come into the picture, and you just now saw that that just by using Taylor series alone, you can write, let's say, a second derivative. I mean, you saw that in the lecture videos that you can write a second derivative del 2t by del x2, written for that m comma n generic node, which is basically for this node as you know the temperature of the neighboring nodes. For instance, del 2t by del x2 written at the m comma nth node can be written as t of m plus 1 comma n minus 2 times of t of m comma n plus t of m minus 1 comma n divided by delta x squared, where this delta x squared is the interval between the grid points. So basically this is what delta x squared look like. Okay, and similarly this length we'll call it as delta y squared, and the length that we choose is at the this is at the discretion of the user basically, but you need to sufficiently choose this delta x and delta y to be to be small enough such that it captures the essential feature in the temperature profile. Okay, see, I will just try to give you a idea of why do you need to have why do you need to have the grid points uh, so close to one another. Okay, but before that, let me first try to make an algebraic equation out of this PDE. For instance, if you now try to write del square t by del y square for the m comma n generic grid is, so you will basically get so the discretized form will be something like this. So it will be n t of m comma n plus 1 minus 2 times of t of m comma n plus t of m comma n minus 1, but this time it would be delta y square. Okay, so all you now need to do is you just need to substitute these forms into this PDE, and you can see that the derivatives are now converted into just nodal values in temperature, which means you just have an algebraic equation. That's it. But again, I say the reason, I mean, the form this you get from this, you simply apply Taylor series. The discussions are there in your lecture series. Okay, so now if you write this by substituting, basically it turns out to be t of m comma m plus 1 comma n minus 2 times of t of m comma n plus t of m minus 1 comma n divided by delta x squared plus t of m comma n plus 1 minus 2 times of t of m comma n plus t of m comma n minus 1 divided by delta y square is equal to 0. Okay, and if you basically choose the fact that for simplicity delta x is equal to delta y, what you'll get is you will just end up getting t of m plus 1 comma n plus t of m minus 1 comma n plus t of m comma n plus 1 minus t of m comma n minus 1. Sorry, this is plus, and then there is minus 4 times t of m comma n, and this is equal to 0. So the equation that you get here, the equation that you see here, this is the discretized equation. As I was telling you, this is the discretized equation for the generic m comma n grid point. Okay, so the unknown here, as I said, is again this t m comma n value of the temperature. So now the point is that at any generic, let's say t m comma n node, you have one discrete equation for temp for you basically have one discrete equation. For instance, I can now write, I can pick, so now I can pick this node as my generic node, and I can do the same discretization and then write the algebraic equation for this node. So in principle, which means I can have m times n equation for all the m times n nodes, and that's how this, and that's basically how you evaluate the temperature in all the grid points. So you will basically have m times n, so for instance, let's say I'm having 20 comma 20 grid, which means you basically have 400 grid points, and for each grid points you can write 400 equations, basically solving for the temperatures at these grid points, just how we just wrote a generic discretized equation for a generic node m comma n. So basically 400 equations, 400 values you are trying to see, solve that. I mean, there are multiple ways of solving algebraic equations. For instance, there is something which is known as Gauss elimination. In this case, you can apply something which is known as a tri-diagonal matrix algorithm. Here you cannot apply actually TDNA, but you can apply, for instance, Gauss elimination. There are iterative solvers. For instance, there is something which is known as Gauss-Seidel. There's also something which is known as Gauss-Jacobi. So you apply all these, you can apply any of these methods to basically, solve the 200, let's say, sets of, algebraic equations for a 200 unknown values of temperature at these grid points. Okay. And this is how, basically the numerical approach works. And that's how you basically, solve the problems using basically using numerical tools like so this discretization that I have done here, this is known as a finite difference method. Okay. And there are other discretization techniques as well. For instance, there is something which is known as a finite volume method, finite element method. And if you are aware of commercial tools like COMSOL, ANSYS, at the back end of COMSOL, ANSYS, this is how they basically solve the problem numerically. Okay. I hope I understand that this is just a glimpse that I have given you. This is just the tip of the iceberg, I should say, in numerical methods. But the other things, these are beyond the scope of a heat transfer. I mean, that's the beyond the scope of an undergraduate heat transfer course. And you can learn more of this if you take specialized course on numerical methods and computational fluid dynamics, where these things are taught in details, basically. Now, but at least I hope you got the idea behind, like, how do you convert a PDE into an algebraic equation, and how do you calculate the unknowns in the algebraic equations, and how the number of unknowns become equal to the number of equations in case of a numerical, in case of this numerical discretization technique using finite difference method, of course. Okay. Now I'll tell you an interesting thing, that what happens if you choose a coarse grid, and why your solution actually does not mimic the actual true solution that it should get. For instance, let's take, I'll give you an example of the 2D problem that we are considering. Okay. Let's say we are trying to solve, or okay, let's not basically give the idea of a 2D problem. I'll give you the idea of a 1D problem, because a 2D is an extension of that 1D problem. I mean, trying to understand the essence is more. So in a 1D problem, you can understand why, what to say. Why, I mean, the choosing less grids than the desired value is will give you basically a wrong solution. That I'll explain to you by using a 1D problem. Okay. All right. So for this, let's say I'm plotting the temperature distribution of, let's say, a rod against a function of time. And let's say I know the analytical solution in this distribution is something like this. Okay. For instance, this is at, so this point is basically at x equals to 0. And this point is, let's say, at x equal to L for the entire rod, so for instance, I'll also draw the rod, okay, which is something like this. Okay. So, so this is x equal to 0 of the rod, and this is x equal to L of the rod. It is just a temperature distribution that I have drawn as a function of x. That's all that I'm doing. But I know that this is my analytical solution. So for instance, at least the temperature variation in this rod analytically, and you have just plot the analytical solution. And this is just a generic solution that I have drawn. It has not got any physical sense in this picture. I'm just trying to give you the understanding that what happens if you choose less number of grid points in numerical while solving the problem numerically. Okay. Now, if we are trying to solve the problem numerically, let's say I'm choosing these grid points uh, in the problem. So now let's say I'm trying to solve this problem numerically. So I have these many grid points. Let's say I'll number the grid points 1, 2, 3, 4, 5, 6. So what you do is you solve the problems. Okay, you discretize the equations into algebraic equations. So here, since this is the 1D problem, you are basically having 6 algebraic equations, and you need to basically calculate the temperature values at these 6 nodes. So what numerical method will give you is that you will have the value of temperature at this point, let's say 6, which is, let's say the value of temperature is denoted by this blue dot. At 0.5 your temperature is, let's say this. At 0.6 your temperature, at 0.4 let's say your temperature is this, and at all other points your temperature values are something like this. Okay. So then if we want to sketch the actual temperature profile, I can basically draw some lines like this, some lines like this, some lines like this, some lines like this. Okay. So this is what your numerical solution is actually giving you, because it will just tell you that what is the temperature at these nodal points, that is 1, 2, 3, 4, 5, 6. So you can now understand that the numerical solution when choosing a coarser grid is not actually mimicking the analytical solution, which basically look something like this. But if you choose grids which are so fine, which are basically so fine to one another, that your numerical solution will now be something like this. So then if you join the dots as what numerical solvers do, you are actually kind of, getting, so your dots will be something like this. Okay. And this will basically continue. So what you are essentially seeing is, if you are choosing very fine grids, you are basically trying to move closer to the analytical solution. And that's the reason why you need to choose at least a certain number of grids such that your numerical solution mimic, the analytical problem of interest, basically, or at least the actual solution, what the problem should actually have. Okay. Now, you can ask me that we can go on and adding more number of grids up to infinity. Let's say I'll have an infinite number of grids, space between these between the endpoints. But that is not a wiser approach, because after a certain number of grids, you know, if you keep on adding number of grids, your solution will not vary very much. And that is the point when you reach grid independence. And in all numerical solver, you need to test for grid independence. And once you reach grid independence, you are sure enough that now if I increase more number of grids, because see, if you are increasing more number of grids, ideally you are increasing the number of equations. Okay. So computational, so basically you are increasing the computational power. You are demanding more computational power. So if you have, let's say, 10 lakhs grid, you need to have very high computational power to solve 10 lakhs equations. But however, if you know that after 10,000 grids, the solution does not vary very much. So a wiser way is that you stop at 10,000 grids, or let's say 10,500 grids, just to be in the safer side. So after 10,500 grids, there is no point in adding the number of grids, because you already know that you still need to solve for 10,500 equation. And adding more number of grid points will just not give you I mean, it will just not benefit you in any way. Okay, because you have reached grid independence at 10,500 equations, basically, or 10,500 grids. So that's the idea behind this numerical solution. For instance, if you choose 10 grids, you already know that the numerical solution that you will get, this will anyway not mimic as this problem that we just now saw. The idea of all this is just centered around the fact that in numerical solution, you are just solving values at the grid points, basically. So if you have a quasar grid, so the connection, that is the connection of these dots, will be so coarse that it will not mimic, the analytical solution. But if you are having a refined grid such that your mesh independence is reached, you can be rest assured that your numerical solution is giving you true result, that the actual solution should, that how the actual solution is should look like. Okay. All right. So this is what I want to convey by this numerical method. For instance, you can also apply, the numerical method to, solve. So I'll not discuss this at this point. This has already been done in the lecture series, but rather I want to discuss this approach. For instance, you can also now use the numerical approach to solve the 1D transient equation. And in that case, you just need to do one more discretization. So for instance, here we did discretization with space. In 1D problem, you'll encounter a term like del t by del t. So if you write this term for any generic m and nth node, this is a variation in time. So you can write this as the temperature at m and at the generic mth node, written for a time which is t plus delta t, minus temperature at the time t, written for the m and n node, m comma n node, divided by delta t, where now you are basically doing a discretization in time, and this is actually known as forward marching in time. Okay. And the discretization that we did here, this discretization, this is known as an explicit scheme that we are doing. Okay. Because we are just trying to evaluate the temperature at the next time step, written in terms of the temperature at the previous time step. Okay. Where delta t is basically the time step, the time interval between two consecutive time steps that we are using. Okay. And you can see, although I'll not prove this, you can see that you'll end up getting a number which is known as a Fourier number. So for Fourier number 1 by 4, I think these explicit schemes actually works well. Okay. Uh, in case of 1D problems, and I guess in case of 2D problems, I don't have exactly a number. I have to check. Okay, for 1D problem, this Fourier number has to be less than half. Okay. If you use explicit scheme in a 1D problem, if you use this explicit scheme in a 2D problem, your Fourier number has to be less than 1 by 4. Okay. You can note these values done. But anyway, this had been already, discussed in the lecture series. So I just don't want to repeat this. Rather, I want to give you the essence of, using why do we use a numerical method and, the related concepts involving that. Okay. So this ends the discussions on conduction heat transfer. I understand. I just gave you a glimpse of solving this equation numerically. And as I said, this is just the tip of the iceberg. But at this point of time, if you are an undergraduate student, this is all that you need to know. For more, detailed information on this numerical method, there are certain dedicated courses involving these discussions. For instance, there is a course called Computational Fluid Dynamics, which you can, you know, take if you want to basically know more on these methods. But at least for this point, in a fundamental heat transfer course, it is sufficient to know up to this point only. Okay. So this ends the discussions on heat conduction. Now, from the next discussion onwards, we will look into a different topic, which is known as heat transfer by radiation, or like radiation heat transfer. And we'll look into the problems involving radiation heat transfer in the next four discussion sessions or next 5 discussion sessions that we'll have. And then that's what we'll do. Okay, so we'll stop here for today. We'll meet at, at the same time 3 to 5 next week using the same link. Okay, thank you very much. Keep watching these videos, and if you have any doubts, keep posting your doubts in the discussion forum. Thank you very much, guys.